Okay, welcome to our first lesson on exponential functions. This lesson is intended to be an investigation, so we're just going to walk through the answers to the investigation. The first one that we graph is the exponent, or y equals 2 to the x. And so we just walk through, like, the y-intercept is, if you sub in 0 equals 2 to the 0, which equals 1, and that's a point 0, 1. So one of the points on the graph is 0, 1. We're going to find that that point is common with most of these graphs. The base function is given from the question. It's a base 2. We can see that this guy is increasing as we move left to right. We talk about left to right because that's what, when we have the x-axis, if we're talking about time, time would start at 0 and then go up, and so this is increasing. Domain is all real numbers. Like, there's no restriction on what we can plug in for our exponent. And the range is an element of the reals, but it has to be a positive number. So we've seen that with exponents. The only way to get a negative is to make a negative base, and so since the base is positive, you're only going to get positive real numbers here. So it's greater than 0. We actually get this horizontal asymptote after we draw the graph. These are our base points. We'll stick from -2 to 2 as our base points for each of them. And so that's in your notes that might not quite be -2 to 2, but those are the base points we actually want to use. If you plug in -2 into 2 to the x, you get a quarter. If you plug in -1, you get a half. 0, you plug in 1, which we already saw. And then we double every time. So if we plug in 1, 2, 3, we're doubling every time. And so it has to have that kind of pattern where we double every time. What this little triangle y is means change in y, or delta y. It's how much you're going up by every time with respect to y. So we can see that on the graph. Here we're going up by half, then 1, and then 2. And then the next would be 4. It's almost like your step pattern, but these are your first differences. Traditionally, after we do the first differences, if they weren't the same, we would check the second differences. But they're clearly not going to be the same either. It's not quadratic. It's not linear or quadratic. And so we actually see that there's a ratio between these first differences. The differences, even though the numbers multiply by 2 every time, but also the differences multiply by 2 every time. So a half grows to 1, grows to 2. It just keeps doubling every time. And so the ratio, kind of like the first differences, are calculated from subtracting a half minus a quarter, or 1 minus a half. These are dividing 1 by a half, or 2 by 1, or 4 by 2, or 1/2 by a quarter. They're all 2. The ratio can either be found, like if you don't have the equation, the ratio can actually be found either on the y values or on the first differences. So that's what this note is. If the horizontal asymptote is 0, which this one is, like, both of these are going to be the same. So the ratio of the first differences and the ratio of the y values are going to both give you 2. But if there is a vertical shift, then the y values aren't actually going to go up in the same ratio. The differences will go up in the same ratio. And what the ratio means is that's our base. It's what we multiply by every time. Just looking at the next one, we got 3 to the x. So a lot of similarities here. The base is 3. Things are tripling every time. So the graph is goes 1/9 at -2, 1/3, 0, 1, 1, 3. If you're graphing these like by hand, like, it's not really that important that you graph 1/9 exactly. This graph's done by Desmos. But if you graph just right around, like just off the x-axis, 1/9 is really hard to draw. 1/3 could be like 1/3 of the way, but you're really just estimating there. Okay, and so you keep going up. So our main points here that we're going to graph are from -2 to 2. Because we don't see the 2,9 point on here because the scale is smaller. But those are the -2 to 2, that's what we're always going to start with to graph. The 327 we're actually probably not going to be able to see, but it's helpful just to notice that, like, it will keep tripling every time. Basis 4 is very, very similar to that. It's just going up by 4 every time. So all these are very similar graphs, except that obviously the 4 to the x is a lot faster. What we're multiplying by is a bigger number, so it's just going to make things bigger every time. Base of 1 to the x, like you might suspect, is actually just same idea. We're just multiplying by 1 every time, and so nothing changes. And so we actually say our range is always equal to 1. Nothing increases or decreases. First differences are 0. Common ratio is 1 like units. It just means we're multiplying by 1 every time. Just because the first differences are the same, and so it actually is linear, but it's also exponential as well. This is kind of the overlap between linear and exponential. And then we start going back down the other way. So if we're multiplying by half every time, that actually decreases. So we still start at 0, 1, but it's decreasing by a half every time. And so we still get that 1/2 to the 0 is 1. So we still get the same y-intercept, but it's decreasing by a half every time. What we're going to see here is this is actually going to be the horizontal reflection of 2 to the x. And we actually seen that before with 2 to the x is 2 is the same thing as a half to the negative 1. And so 2 to the x will be the same, or 1/2 to the x will be the same as 2 to the negative x. We'll see that in the next lesson. 1/3 to the x is getting smaller faster, so it's multiplying by a third every time. You're actually losing 2/3 here. Multiplying by a third means you have a third left. If you take 100, multiply by a third, you have, say, like 33.33. You've lost 2/3. So that's the decrease. We're going to come back to that in the applications. The ratio is still kind of 3. It's just going back the other way. So the easiest way to see this, rather than doing like a fraction, reducing the fraction, you can just see that, well, we're tripling that way, so that means we're doing a third this way, and so we've got a third. Okay. So what ordered pair do these have in common? They all have the point 0, 1. The graphs that are increasing are 2 to the x, 3 to the x, and 4 to the x, with 2 to the x being slower and 4 to the x being the fastest. Decreasing is 1/2 to the x and 1/3 to the x, with the 1/3 x being the fastest decrease this time. 1/2 to the x is the slower decrease, and then neither is the 1 to the x. For it to be increasing, the base has to be bigger than 1. For it to be decreasing, the base has to be less than 1. And explain why there's a graph that shows neither, because there's no change. It's just multiplying by 1 every time. Okay. How the value of the base determines the shape of the graph. The base is what you are multiplying by each time. You can increase very quickly, so you can have like a 10 to the x, and the fastest we have here is a 5 to the x, like increasing by 5 every time. This would be 5, and the next one would be 25. That guy's the fastest increase. It's the largest b value. This guy here is the slowest increase. It's still increasing, but slowest. It's a lower b value, and we can actually see what the b value is. It's potentially, this one is 2 to the x. This one is 5 to the x. This one here is the fastest decrease, and so the other way, like since this has a negative 1,5, this is a 1/5 to the x. But the b value is still above 0. It's 1/5. And the slowest decrease, if you go to the 1 point, this would be a 1/2 to the x. You can see this is the 1/2 to the x graph. This is the 2 to the x graph, and they're all horizontal reflections of each other. And that's that exponent law. With a negative exponent really means flip it and make it a fraction. Take the reciprocal. Okay. So some practice questions. Number 1, it's looking at doing first differences, second differences, common ratio. You can look at the examples there around that page. Number 2 is just looking at graphs. The practice is pretty short after you get through the tables. Okay.